guy from the
Okay,
front.
maybe we should start.
A few more?
Yeah, I think so.
Camera is okay? The camera is there. We have to know the camera. Yeah, you are being broadcasted all over Israel. You have a competition with Bibi Netanyahu. I'm sure you're gonna win.
Who is that?
Okay, guys, we are glad to have all of you here for the panel. And the panel is on free will, time, quantum, and the many worlds. And we have all these distinguished professors. Everybody here is a professor. And I will introduce them really very briefly, otherwise it will take the whole evening. So I'll do it alphabetically, even though it happens to be the most senior one is Yakir Aharonov. So Yakir from Tel Aviv University, he has made numerous contributions to the foundations of quantum mechanics, including famous Aharonov bomb effect, weak measurements, Aharonov kasher, Aharonov Anandan phase, protective measurements, the two-state vector formalism, which is a competitor to the many-world interpretation. You're going to talk about it, and many other things. So Yakir, thanks for joining us. Valia, Allori. So Valia from Northern Illinois University. She's a philosopher of physics, and she made contributions to the foundations of quantum mechanics with the aim of understanding metaphysical commitments and epistemological limitations if we live in the quantum world. And she contributed also to other things, many other things, like the study of wave function and free will in quantum mechanics. So thank you for. We decided that you contributed also to free will. So.
Yeah. No, I do have a paper on that. Yeah.
Nicolas Gisin from the University of Geneva. He has actually made contributions also to experimental physics, both experimental and theoretical contributions, long distance quantum communication, violations of Bain inequality and teleportation at long distances, single photon detectors, as well as many theoretical results in quantum information. Thank you for joining us. Renato Renner from ETH Zurich. He made numerous contributions in the field of quantum information, security of quantum key distribution, quantum cryptography, cybersecurity, in recent years to many world interpretations and issues related to the foundations of quantum mechanics. So also thank you for joining us. And David Wallace from University of Pittsburgh. He's a philosopher of physics. He's been developing the Everett interpretation of quantum theory. His book came in 2012 on the emergent multiverse, contributed to many other things, philosophical and conceptual topics in quantum mechanics, quantum field theory, statistical mechanics, general relativity, and more. Okay, so thank you all, and the plan is as follows. We have about 1 hour and 15 minutes, otherwise after that the gates will be closed and we are stuck. There will be questions to the panels. I'll ask you alphabetically to answer them, and after we'll have a few minutes to ask questions from you. Okay, so that's the plan. And I will start with the first question to Yakir. And the question is obvious. I mean, we have a pretty good intuition about what is the classical world, since we have a lot of experience from interaction with it in our daily life. But we have no good intuition what is the quantum world. So can you describe in your own words, sentences, what is our quantum universe?
I will start by saying what it is not. When everybody tries to describe quantum mechanics by saying that a particle can be at the same time at two different locations. And I believe this is complete nonsense. When you say that a particle is at the same time at two different locations, what does it mean? The particle has a given mass and a given charge. If the particle is at the same time at two different locations, where is the mass and the charge? There is a possibility to say that half of it is here and half of it is there. That is not true, because if half of it was in one place, and half of it was another place, I make a measurement and suddenly find it here, then the other part has to come quickly there, faster than light. That can't happen. So the particle, the mass and the charge must always be in one location. We may not know where it is, but it can never be at the same time at two different locations. So we have to explain interference, not by saying that the particle goes through both lists, but instead to look at the Heisenberg representation and see that the particle goes through one slit, but it has another property that tells what will happen later in the interference. This property is a non-local property. It has non-local equations of motion. And by pre and post selection, we can find indeed through which slit the particle went, even though we still have interference. So I think that the best way to describe what the difference between classical physics and quantum mechanics is not by saying that in quantum mechanics the particle is spread and behaves also as a wave, but rather than to look at the dynamical difference between classical and quantum mechanics. The dynamical difference is described by commutators instead of Poisson brackets in the dynamics, and the commutators have the property that you have non-local equations of motion. For example, in the A-B effect, the particle can go one side or the other side, but it feels non-locally the magnetic field that is not there because it has non-local equations of motion. So if you ask me what quantum mechanics is, it's new physics, new dynamics that have non-local equations of motion.
Okay, thanks for this answer, non-locality. And Valia, you are next. And do you agree?
Yes, I actually do. Yes. Hello? Yes, yes, okay. Yes, thank you for actually saying exactly what I was going to say.
Oh,
So,
really?
yeah,
Oh.
I totally agree with that. Right, so yes, so I don't really know. I wish I knew what the quantum world is, but I don't. In my, experience, I try to make sense of that in many ways. And I mean, it started off with, as I mentioned, as a student, as in many orders, it didn't work out very well for me. So I tried to explore other ways. And so I get to the point in which I was asking myself, okay, what do you want to know about the quantum world? What do you like? I mean, what it means for you to understand what the quantum world is like. So what I wanted, so my answer to myself was that I want to know what matter is made of. I mean, and how it moves. So I want a dynamic. I want a clear ontology. I want a clear dynamics, and I want to explore what the consequences of these dynamics are. And it actually straightforwardly follows that it's not local. And so yeah. So if you ask me what's the heart of the quantum is, I would not say quantization. I would not say anything other than non-locality. So yeah, so I don't have any much more to add to this. Thank you.
Nicolas, do you agree? Non-locality.
To make it more interesting, let's say no.
Okay, good.
But let me start from a slightly different point of view. Yakir said, okay, classical mechanics, we understand. We have certainly a good feeling that we understand it, and actually we have been selected at universities by our ability to claim that we understand it. It doesn't mean that we really understand it. And I think anyway, as I said also during this very nice workshop, classical mechanics, if you really express it with the standard mathematical language, Platonistic language, with real numbers, with infinite information, all that, then everything is super well determined, and chaos is deterministic, and we have all this understanding that, again, we have been trained to follow. But if you change the language, which doesn't change anything about all the predictions, but you move from Platonistic mathematics to intuitionistic mathematics. I mean, intuitionistic mathematics has only finite information at any finite time, and then actually the numbers, in an intuitive sense, the digits come one after the other as time passes. It's a bit more complicated than that, but essentially time plays then a fundamental role. And although all the predictions are the same, all the computation you can do lead exactly to the same predictions, certainly you see that also classical mechanics is intrinsically indeterministic. And then, the facts have not changed, the predictions have not changed. change the language, and then suddenly you are with a completely different worldview offered by classical mechanics. And I think it's interesting because then some of the quantum aspects that are so disturbing or surprising, counterintuitive, whatever, you have them already in classical mechanics. And I think that's interesting because we have this intuition that we understand classical mechanics, but then we have that with all these randomness or indeterminacy and indeterminism both, that is so difficult to swallow and understand in quantum mechanics, and even some part, as I have explained, of non-locality, not all of non-locality, but part of it you also have in this alternative view of classical mechanics. So I think that's a nice way of saying no to you. Sorry.
You are saying probabilistic but local.
No, it's not local.
It's not local. Do you agree with him?
Yeah, but it's not only the dynamics. It's a bit more than that.
Okay, but actually,
Bell inequality, I don't think it's only the dynamics. AB effect, I would agree with Yakir. For Bell inequality, I think it's not enough.
Yes, it's real for non-local. Lev, where are you? Okay, Renato. Please.
To make it even more interesting, I should say that I completely agree with everything that Nicolas said. I also found it very interesting, but I would say it's completely irrelevant. And the reason is that, I mean, we are physicists and we want to describe the world, and we know the world is not classical. So it's interesting maybe to think about the classical theory, but I think we should focus on quantum theory. And that, in a sense, I agree that we see things in the classical theory already that usually are attributed to quantum theory. But we could also now turn it around and go backwards and say quantum theory already tells us that the amount of information we can have about an object is anyway finite. I think there are many instances where we see that. And that implies that the classical theory, if we now go back from the quantum theory to the classical theory, has to inherit that feature. And then we are back where you are. And I would then agree that classical theory should be the way you just described it. I mean, we never have precise information. We should take this intuitionistic approach and so on. But yeah, the question is, what's the reason to even go back to the classical theory? I don't see it. We agreed yesterday we have to disagree to make this interesting.
Okay, so what we learned is that you think these are two different theories, but we still didn't understand what's the difference. Is it non-local? Is it probabilistic? What's the difference? And then today.
Oh, I should first answer to that. Okay, maybe the second thing I should say to not answer your question is that for me quantum theory is an not yet completed theory, because we know it's not always consistent. At least I know that, and some people don't believe me. And therefore, I mean, I think we have to admit that when we talk about these questions. I mean, we talk about questions usually assuming that we already have a complete mathematical framework. But I would disagree that we have that for reasons that have to do with the thoughts experiment that some of you probably know that I proposed.
Maybe.
It's a blessing or curse to go last. I mean, let me say what I think the world looks like if you take the quantum formalism fairly literally, and that's leaving aside the possibility that we might have good reason to change the formalism, whether in two-state directions or through hidden variables, whatever. But given the formalism at face value, the formalism has states, that is, ways systems can be, and there are states in the formalism that seem well set up to define things like there's an electron here, and states in the formalism that seem well set up to describe there's an electron here. And the formalism has a systematic superposition principle, so that whenever I've got state 1 and state 2, I've got some ability to have a state I can call 1 plus 2, or weighted versions of 1 plus 2. And how we make sense of that depends what we think states are. And in physics generally, in classical physics, come to that, we've got two very different notions of states on the table. One of those notions is representational, i.e. the state represents the physical properties systems actually have. So if I use different states to describe a system, I'm saying the system has different features. And the other notion, which we also have in classical mechanics, is probabilistic, where we might say different states represent maybe different levels of knowledge about systems, or maybe they represent different fractions of systems having different properties. The probabilistic reading of the quantum state doesn't really look viable for familiar reasons. The interference effect of quantum mechanics seem to make it very hard to suppose that we can understand quantum states as just saying, well, when I have the quantum state here plus there, I just mean either here or there, and I don't know which. So I'm going to, timorously disagree with Yakir and say I do want to say I think the natural and available reading of what the quantum formalism says is that indeed, if I've got a superposition of here and here, then in some appropriate sense the particle really is here and here at the same time. So where's its mass or its charge? Well, if it's here and here at the same time, then its mass, say, is here and here at the same time. It's absolutely not, for exactly the reasons you give, spread out half and half. It's here and here at the same time. So what does that mean? Well, mass is let's do charge. It's more physically realistic, and even philosophers gesture in the direction of experimental realization. What does charge do? Well, operationally, charge is a thing that pulls other charged particles towards it. So if the charge is here and here at the same time, what happens if I bring another charged particle? Well, that particle goes this way and that way at the same time. So now, as soon as I let my charged particle interact with some other stuff, now I've got both charged particles here plus both charged particles here at the same time. And if a third charged particle comes along, I have something like the same thing going on. And this is entanglement. This is just the fact that if you let the dynamics play out, then systems of superpositions organize themselves into entangled superpositions, where you end up saying things like there's the system is a whole bunch of basically classical and localized goings on, plus a whole bunch of other classically localized goings on at the same time. And that structure writ large is the many worlds structure that I think is what you naturally get is looking at the formalism of quantum mechanics. Those worlds aren't coming out to put them into formalism, they're coming out at the emergent level, because that's how dynamical interactions and entanglement cause individual superpositions to magnify up and cover your whole system.
Okay, thank you. So it seems that the experts are in disagreement, and that's actually the reason for the saying never trust the experts. Okay, so let me move to another one, which is the current workshop is about many-world interpretation, and in a many-world, the universe is single, complicated wave function, highly entangled, and it evolves deterministically in time. So the question is, if you are a believer of the many-world interpretation, is there a room for free will in this? And since you are not a believer, for you the answer is easy. But
I can't answer this. I don't believe in the many worlds, so this question is irrelevant to me.
No, but if there is, you can ask about free will in your formula.
Free will in the two-state vector.
Free will is another story. I thought you want to
It's
go.
free will in the many world, but for you it will be free will in your.
Oh, I think free will exists, and the fact that the physics of today doesn't allow us to have free will, meaningful free will, that means that there must be some changes. And I will describe maybe a little bit of that in my talk on Monday. Okay?
Okay. All right. So, to me, okay. So, I mean, I'm certainly not a philosopher of free will. I had that paper in which I'm actually dismantling in other positions. So, but I mean, let me just say this. My intuition about this is that regardless of what kind of theory you have, that is in which you have, matter governed by laws, there is no hope for any kind of, libertarian free will. There is no way in which you can get around it. If you want to have a free will in which you can say, oh, I could have done otherwise. No, because I mean the laws are governing what you're gonna do. They are, they're not up to you. either whether they are deterministic, so there is only one future given, only one past and only one future, so you don't determine that, you don't have any saying in that, the laws are determining that, and you have nothing to choose more than just like it's coming from your, desires and beliefs, so kind of a compatibilist free will. You don't have any more than that. So in a deterministic universe like many worlds, you don't have it. Maybe with some maneuvers, you may have some, but never of the kind of, that some people would like. And that's also true in case of stochastic theories, in deterministic theories as well. You may have multiple futures, but, they're not up to you. So you're going to end up either here or there. But not because you choose to. It's just like something that happens.
Sure.
So, yes. So, this is pretty much what I think. Unfortunately, I wish I had free will, but I don't. So I had to say it. I was governed by laws.
Yakir wants to add something to the free. So he has a free will to add something to the.
Okay. Maybe I will explain more what I believe about free will. I think that in classical theory, of course, if our brain is a physical system, there is no room for any possibility. Quantum mechanics opens the possibility that the past does not determine completely the future, so there are a number of possibilities open for me, but quantum mechanics dictates that the choices between these possibilities are completely random. It is like throwing a coin, and that is not a meaningful free will. So my hope of changing something is to say the following. Our brain is such a complicated system that I believe that there is no way to make a copy of it. Suppose we admit that, then if there is no ensemble that I can decide according to probabilities, if there is only one example where I have to make a choice, then the quantum probabilities, the quantum Born rule, does not apply for this individual case because there is no way to check it by an ensemble of identical me's that have to make the decision at the same case. So I believe that if indeed it's impossible to copy my brain, I am free to choose now between the options that quantum opens for me, not according to the probability rule, but according to some other way that will mean what a free will is.
Okay, that's interesting. Nicolas?
Okay, thank you. So maybe first about the many world. So I'm a researcher, and as a researcher, I love problems and open questions, much more than solutions, and especially I don't like, solutions that pretend to have the answer to everything. Then it's nothing to do if the answer is already there. So, for instance, the mini world I think is super pretentious. And it's not really something which I'm attracted to because I want open problems. And I think indeed, and on that I really stand totally with Yakir about free will. All of our physics of today, whether it is classical or quantum, whatever, there is nothing here which allows us to believe in our standard understanding of free will. Of course, now we can invent compatibilist free will or things like that, or what Yakir also just said. But clearly, we don't really understand free will. However, free will exists, which only means that determinism cannot be the ultimate answer because we would have no free will, and we have free will. Just randomness is also not a possibility because then it would be a meaningless free will, so it wouldn't be a meaningful free will, so Yakir just said. So there is something else. And so when I say, for instance, indeterminism, I'm not saying it is random, I'm just saying it is not deterministic. Or I could also say in randomness or non-randomness, which would again say that there are different possibilities. Maybe I would even make one more step here. Free will, as I have said sometimes, comes first in the logical order. You need free will to make sense of, you need free will in order to be able to accept or to reject an argument that you hear. You are hearing many arguments tonight. If you have no free will, how are you going to decide which argument makes sense to you and which one don't make sense? So you need free will actually to start thinking rationally, to start to do philosophy and to start to do science. So maybe it is actually not physics that should explain free will, but free will that explains our possibility to do science and philosophy.
Thank you. Of course, the first question is whether I even believe to have free will, because otherwise the question doesn't arise. And okay, I'm not even sure about the answer there, because sometimes I want to do things because I freely choose to do them, but I didn't choose that I freely want. I didn't freely choose that I want them. So you see, there are these problems that we sometimes feel we are influenced by something, and we didn't choose that influence. But to relate that to physics, I think we know so little about free will that we can at most maybe give a criterion that tells us that a physical theory allows or has place for free will. And here I, of course, agree with what, for example, Nicolas said, that if you are in the deterministic world, there seems to be no place, at least for a strong form of free will. Now, if the world is not deterministic, then there is this place, and I'm not sure how to really make this distinction between random and not deterministic. I agree there should be such a distinction, but I think if a theory today is not deterministic, it appears to us to be random, and this randomness could, of course, now be something that just appears random, but maybe someone who knows why something was done can realize it was freely chosen in a way that we couldn't understand. So for me, the question is in all the interpretations now, whether they allow for free will. And I would also agree with Nicolas that free will is a precondition for physics. Okay, that's maybe not such a strong statement, because I don't know what free will is, so it's an empty statement in a sense. But I could weaken it now and say non-determinism is a necessary condition to embed free will into a physical theory. And if I now go to an even explicit form of non-determinism, which is randomness, then I would say randomness is clearly a condition to do physics. All experiments, everything we do, relies on the fact that we can, for example, randomly choose a sample on which we test things. So randomness is a precondition, and randomness is non-determinism, randomness requires that it's not deterministic, and the same is true for free will. So I see this connection that we should make, that we need somehow non-determinism to do physics.
Can I ask a quick? Oh, sorry.
Yes.
Yeah, just a quick question for Freddie. If you need randomness for experiments, do you think if I used a pseudo-random number generator in my computer instead of genuine random noise, would it matter for science?
If you are paranoid, yes. Because then, of course, the world could just be arranged in such a way that it matters, and I just see results that are completely non-representative. Now, you said something in the introduction that I do cybersecurity. I have no idea what that is, but I do cryptography, and as a cryptographer, one usually thinks in this paranoid way, because there's always an adversary who tries to set up the world in a way that hurts us. So that's why.
Yeah, I shouldn't have asked the cryptographer that question.
Yeah. Okay, maybe the last thing I should say is that the implication of what I say, of what I said before, is that I wouldn't like an interpretation like Bohmian mechanics, where you have clearly a completely deterministic evolution of the world, and therefore no place for free will. For many worlds, I simply don't know whether it's deterministic or not. It is on a certain level and another not, and maybe I give my microphone to David and say more about that.
Thank you. Well, I'm going to give a very boring philosopher's answer, actually. And then I'll say a provocative thing about the many worlds theory I don't believe at the end. But the boring thing is I actually think that these questions don't really turn on anything specific about the many worlds theory at all. I think the general debate in philosophy, very long time, about whether we have free will or not, just turns on rather general features of whether we have sort of microscopic mechanical theory and whether that's a problem for free will. My view is that we don't have a problem, that there's no incompatibility between any form of free will we like and would like to have, and anything in our physics. But I don't think I need any particular, I'm not drawing on any particular expertise in quantum theory to say that. I mean, the elementary thing I'd say would be something like this. I think free will ends up being being what Dan Dennett calls adipety. It's something that's ambiguous between something that's innocuous and something that's provocative but clearly wrong. And I think if you try to pin down a meaningful notion of free will that actually is a meaningful thing we could want to have, but which is imperiled by the microdeterminism of the world, I think you end up not managing to cleanly define a concept. And I'll kind of illustrate a little bit. I mean, I'm at this panel freely. I chose freely to come to this panel. Nonetheless, Lev was able to predict on the basis of Lev predicted on the basis that I said yes to an email. Where are we? Back in June, Lev predicted with sufficient confidence that I was going to be at this conference that he could advertise my presence and put it on the program. And rightly so. Lev's extremely reliable prediction that I turn up to this panel was correct. It was not a random process that I turned up at this panel. And yet I came here freely. Now, we can think of ways I couldn't have come here freely. Maybe I didn't come here freely because I didn't realize that Lev had embedded hypnotic code in the email. And when I looked at it, I was programmed by Lev to come. Maybe, actually, this is a hostage talk, and actually I was brought here at gunpoint by Lev goons. Maybe some random number generator installed in my brain actually determined, took control of my body, and on 50-50 odds brought me here or not. Now, in all those situations, I wouldn't have had free will. And it matters. I'm glad those things didn't happen. I want to have the kind of free will that meant I could come here freely to the panel. But the sense of freedom that's doing the work here is that I came here for my own reasons. The reason I came was because I formed a desire to come and wanted to come and chose to come. Now, the fact that those wants and desires and choices are ultimately physical processes, and somebody with a sufficiently good, perhaps impossibly good microscope could predict it, seems neither here nor there. You didn't actually need an impossibly good microscope to predict I was going to come. Like I say, you could predict it very reliably just from my saying yes to Lev on an email. So my very boring and original view is that there isn't the meaningful, sensible notion of free will is not undermined by indeterminism. That said, if you don't buy that, if you have a much more mystical take on free will, which I think you shouldn't have, then probably the Everett interpretation is your friend. Because the problem for free will is that it's in the sort of, I think, romantic sense that doesn't make any sense. It's supposed to be incompatible with determinism because somehow if there's determinism, the future is completely predictable, but yet somehow randomness doesn't help. Well, in the Everett interpretation, if there's going to be a branching event, I can totally reliably predict the third-party future, but nobody, not even God, can predict what I will happen, because there are two branches, there are two versions of me. There's no third-party way of picking out which one I am. There's no third-party fact about which one I am. So if you care about the romantic notion of free will, I suspect there are deep resources you can use there to find a theory of free will that works in the Everett interpretation doesn't elsewhere. But you shouldn't waste your time on this, because the romantic notion of free will is wrong.
Okay, yeah, we will have some time for questions, yeah, but let me make a quick summary. I mean, on one side, people would have liked to have free will, but we don't understand how to find it in physical theories, and the other side gave up on the romantic free will, and that's easy.
But the non-romantic one is worth having, and we have it.
And we have it, of course. Okay, so next issue is the issue of time. Okay, so question is, what is the meaning of time in the quantum world? Classically, we have a pretty much good understanding of what we mean by time, but quantum mechanically we have no idea whether it exists and what's the definition. Is it fundamental? Is it emergent? What is this quantity? Yakir, this is really a good question for you.
Well, the problem of time is a very difficult problem. We certainly experience time by saying that there is a definite present now, and then there will be another present, and the present that was now will be past, etc. That is not the way that physics describes time. physics describes time as a block universe that all times, in a sense, coexist. Einstein wrote when his best friend, one of his friends, died, and he wrote a letter to the widow, and he said, "Don't worry too much about it, because all times exist, and the time that you were with your husband continues to exist. Don't worry about the fact that you think that that time is more important. That's just an illusion." But of course, Einstein himself was very unhappy about it, and I think that there is really still an opening for a new description of time that is different from the time that we describe now in physics. There is another example of our experience that tells that something is still missing of the physics today.
Thank you. Yeah. Okay. So I kind of disagree with the question. So you said that it's clear in classical mechanics what time is. It's unclear in quantum theory what time is. I think it's unclear what time is. Period. I don't think that just simply because we go to the quantum theory in which nothing is clear, right? There's also time clear. And I don't think necessarily that if you think you have an understanding of time in classical mechanics, then you lose that kind of understanding when you move to quantum theory. I don't think you do necessarily, and I don't think that any. So maybe if you standard quantum mechanics, and one crucial difference with the other variables, there is no time operator. So that's maybe why. But I don't really understand standard quantum mechanics. So, but as far as I understand the other theories, many words and the others, it doesn't seem to me that there is a substantial difference in the way in which you're using time as in classical mechanics. You're just using something just to implement the dynamics. So and this can be compatible with whatever you prefer the view of time is. So I wouldn't. So there are so many mysteries in quantum theory. I would not add the time mystery to that. So yeah.
So what's your definition of time? Because in half an hour we finish.
Yes, exactly. Right. So yeah, I don't know. I wish I knew. But whatever the definition that you provide in classical, it seems like if there is something which more uncontroversial, something that most people would agree it's similar, that's what I would have said before your question, right? So if there is something that some kind of get preserved from classical to quantum, I would say the time is, right? It's just like at the bottom of the differential equation or something, right? That's what you use. It's not quantum. Yeah. So, but I don't have any profound idea about what time could be, neither from the quantum nor from the classical side.
Yeah, okay, so this time I have to say I agree mostly with what has just been said by Yakir and Valia. So first, indeed, time is certainly one of the most difficult questions that physics is facing presently. And it's also one probably of the most important. Possibly it has a connection with free will. I'm not really sure about that. But certainly today, if we want to put together quantum mechanics and quantum mechanics, which I see as indeterministic theory, and relativity, which is a kind of super deterministic or strongly deterministic theory, it just doesn't work. And so I don't know what to do with that. Somehow my intuition is that there are more than one time. There is this time which is just an evolution parameter. We could call it Einstein time or Parmenides time, where actually nothing happens. What is important is just being. But then there is creative time, where what is important is becoming, is the change. So this kind of time could be identified with the accumulation of little act of creation of new information. The time would really be accumulation of new information there. And this kind of time, maybe we'll call it Heraclitus time, is what is completely missing in physics. In some formulation maybe of quantum mechanics, when you have a measurement, you could say that is new information gets created, or with my beloved intuitionistic mathematics, you could also say there's a continuous creation of fresh information. But this is really not yet included in today's physics, and I think whether it is now two-time formalism, a creation of new information, but Today's physics only has this boring evolution parameter where nothing happens. And I don't think this is time. So we need really to introduce a new concept or new concepts of time in physics before we can make some significant progress.
Thank you. I think I discussed questions like these with Nicolas a lot, and I agree. So I cannot make this more relevant. I think it's even relevant. So for me, time is a collection of very different concepts. And this is also reflected by the fact that time is represented in very different ways in the different physical theories. And if you go and look what's time in quantum mechanics, it's quite different from what time is in general relativity. And it's again a very different concept in thermodynamics, for example. But it, in all these theories, plays a role, but in a very different way. And I think this is not just a technical distinction that we represent it differently mathematically, it just captures different aspects of what we summarize by this term time, which is probably a very broad term, which I think also became clear from the answers before. Time has many aspects. And maybe one aspect I would just maybe want to make a last comment on is the aspect of the arrow of time, that it's directed. And that's, for example, an aspect that we clearly don't see in any of the fundamental theories of physics, like electrodynamics, classical mechanics, even quantum theory, at least in my understanding, where it's unitary, doesn't have an arrow. But clearly this arrow is there. And I think the answer, and that's, I think, the point where I agree even most strongly with Nicolas, and also what has been said about, for example, the two-state formalism, but Nicolas was very explicit, it has to do with information. And so time is not a property that we can understand by understanding a physical, or by exploring a physical system. It also has to do with the information we have about that system. And that's usually a part that is not described by a physical theory. A physical theory usually excludes the user of the theory from the description. It's somewhat implicit. And actually that's maybe a reason why I personally am very interested in quantum information, or generally information theoretic approaches to physics, because they try to bring back this notion that also the information we have about the system is important, and not only the physical system itself.
Okay, well, I largely agree with Valia, but she got to go first, so let me try to say something different. I think what you think about time in quantum mechanics turns a lot on how you think about the quantum measurement problem. I think, and in particular, it turns on whether you have sort of operational or informational takes on quantum mechanics, or whether you're more inclined to something like many worlds, or indeed something like Bohm's theory, where I've got just a playing out of a dynamical process. If you think that the notion of intervention and action is a core part of what quantum mechanics is about, then I think there's a kind of directedness in our deepest physics that comes from the very fact that we're formulating it in terms of intervening and operating and modifying it. So on that sort of interventionist conception of what physics is doing, then I think time is doing something that really is radically new and not present in our classical understanding and in a Newtonian understanding. I don't think that. I think that unitary quantum mechanics is a perfectly good dynamical story, that the complex physical systems and in principle are modelable within that. From that point of view, I think standard quantum mechanics, here I agree with Valia, has the same kind of parameter dynamical notion of time that Newtonian physics had. And I think standard quantum field theory, likewise, it has a classical background space-time on which all of the exciting quantum goings-on play out. And I think if we insofar as we understand time in classical field theory, we can understand it in quantum field theory. If you buy something like the Everett interpretation or another story where it's sort of dynamics first, not intervention first. Where I think quantum mechanics makes it interesting again, even on the dynamical conception, is when you start looking at quantum gravity. So in the classical world, we had a background notion of space-time, but then Einstein told us to replace that with a dynamical notion of space-time, where we still have a notion of dynamics, of one state of the universe bringing about subsequent states of the universe, or whether you think that's a time reversible process is up for grabs, but in any case, of a dynamical process that relates to different stages of the universe. but the notion of the flow of the temporal interval and where things are in time became something that was part of the dynamical process. Take that to a quantum universe and try to build a quantum theory of gravity, and it starts being quite difficult not to say that we can somehow have the universe having two dynamical geometries at the same time, so to speak, or coded in one and the same state. And so once you take that dynamical conception of time that we get from classical general relativity, and you try to bring it into quantum theory where we have a superposition principle, and where we can't have a background against which things play out, there I think there are deep mysteries that we're still only starting to understand.
Thank you. That means that time is actually an emergent quantum.
In quantum GR, very possibly.
Yeah. Okay. Actually, two of you are from Switzerland, and I always thought that the Swiss watch is showing the time very accurately.
Yeah, but it's the boring time. It's the boring time, not the creative time.
Okay, last question, and then after that we will just open it. And so that's actually a question, I think, from Lev, because he's worried. The many-word interpretation is consistent with the empirical evidence, it's deterministic, has no action at a distance. It's actually a great thing. So why we are not in consensus? What is missing?
And also I understand the question you asked.
By Occam's razor, this is the best solution. So why we are not in consensus? Simple, does everything.
It's unbelievably complicated. I mean, you create a monster without any experimental evidence. For example, suppose that I use a quantum computer to write a number that has 10 figures in it. That will create a world 10 to the 10 worlds. That's more than the whole number of particles in the world. So here, there is inside a box a piece of paper that has these 10 figures in it, but there are 10 to the 10 pieces of paper there, superposition of it. To create a monster like this, with no problem at all, is something that I don't like. Also, I don't like the fact that my wave function has a tail at the street there, and there is a world when I'm just being run over at this instant of time. And the world exists, even though it has, according to Lev, much less importance, but it's there. While if I believe in probabilities, I don't worry about it, because I have to make 10 to the 10 experiment before I would see it. But in the actual many-world picture, it happens all the time, and I feel very unhappy about the fact that one of me is being run over just now. So that's why I don't like the many words.
Okay, so I'm not going to repeat what I said in my talk, but I mean that in my talk I was trying to understand better why is that people are disagreeing about all this interpretation. But so I'm just going to say that in a different way. So I mean, like all razors, Occam's razor can be dangerous, right? You can cut in places which you don't really want. So so we prefer simplicity in the best of the possible worlds that you can have. You would like to have a theory which is simple, both at the mathematical level, the ontological level, how you write down the theory, and also at the explanatory level when you try to connect the theory with what you observe. Right, and then the explanatory part in which you go from what you have to write down. I mean, what you have written down is just like a mathematical set of equations. So you want to give an understanding, right? These are mathematical symbols. What do they represent? You do this, right? You want this to be simple and straightforward. And then what you do about this, you probably end up with a theory which is at the microscopic level of some sort, some scientific image that doesn't straightforwardly represent what you observe at the macro level, what you experience at the macroscopic level. So there has to be a story that brings you from the microscopic level to the macroscopic level. So in the best of the possible worlds, you want both something that you write down, which is simple and straightforward, as simple as possible, right? And a simple explanatory story. Okay, unfortunately, we don't have such a theory just yet, right? Because we do have the many words theory, which is extremely simple when you write it down, just one equation, one side, right? Extremely simple. But then, in the moment in which you go from here to the macro level, everything happens, right? I mean, literally, right? I mean, there's so much work to be done, right? So it's just very, convoluted. Everybody's disagreeing. It's a lot of fun, right? But maybe we don't want fun from science. We want understanding. I mean, we also want fun, right? But also understanding. So on the other side, the theory that I tend to favor is not as simple as the many word, right? I mean, the tidal wave theory. It's not as simple as that, or the GRW theory is not as simple as that. But at least for sure in Bohemian mechanics, the connection between the macro and the micro, the micro and the macro. Sorry, my Italian roots are coming out. It's much easier, much more transparent than what happens in the many word. So on one hand, you have simplicity on the mathematical level and a lot of work to be done to interpret and connect it to experience. On the other side, you have a little more complication. You may want to say a lot more complication on the mathematical level and the representation level on the theory, but more straightforward understanding. So that's why we probably disagree. People are preferring different simplistic consideration. At least that's what I hope that people are disagreeing about, and that makes sense to me. This is my way of making sense of all these, discussions that we are having at this table. So, yes.
Thank you. Yeah. So why is not the many world interpretation not the universal accepted interpretation? And I think there are two main reasons, or maybe three. So the first one is simply that it doesn't make new predictions, and physics is an empirical science. Of course, if there would be a very clear new predictions, that would settle the entire discussion. And secondly, in many world interpretation, as I understand, it doesn't really open new questions. Usually, if you have a good answer, it should open many new questions. As I already said, I prefer the open questions to the kind of ultimate solutions. So I don't think it feeds enough for the physicists. It doesn't give us enough food somehow. But then there's a third reason, which is maybe much more debatable, which I would like to put on the table. It's a connection with free will that we already mentioned before. So classical mechanics clearly doesn't explain free will, doesn't describe it, but at least it leaves the possibility open. Already Descartes was saying, there is possibly something that he gave a name to, this pineal gland, that would be just a kind of little interface. Of course, I mean, it's not a biological or physical interface, but at least there is the logical possibility to interfere, because classical mechanics doesn't need to be presented as a complete theory. You have the possibility to believe that there is some room coming from our side. In the many world, where everything gets entangled with everything, of course, I exist in this world, and probably most of the world that don't exist any longer, but there are some whatever. It's kind of impossible to come from the outside, because there's no room left to come in and say, okay, now I can interfere. I can decide to make an experiment, or I can decide to go for a drink, whatever. I cannot do anything. It seems it's such a block, not in the sense of the block universe, but everything is entangled. There's no way to move in that, because anyway, if I would try to move here, I'm also moving in all the other worlds if I would have something like free will. So it seems to me to be a dead end, simply. And I don't know what's this 94% of physicists who don't believe in the many worlds, but I guess for many of them, there's just not enough food to do new physics with that.
No, this sounds to me emotional reason, no? Do you have analytical reason for this?
Maybe you have a social reason. Actually, I think I told someone today this story, that when I published a paper I have with Daniela Fraufiger, which proposes a salt experiment about the inconsistency of quantum theory. I got enormously many emails, but there was one type of email that was predominant, which was an email starting with the following thing: doesn't this salt experiment exactly prove that my interpretation is correct and all the others are wrong? And I think this shows very nicely that people, scientists, us, I mean, including me, probably, once we believe in, or once we have somehow a preference, we try to constantly confirm it and see all the evidence in favor of that and not look at the other possibilities. So I think it's actually a good thing that we don't all agree on many words at this point, because this plurality that we have via that allows us to think in different ways, look at the problem, for example, the measurement problem that we all want to address from different perspectives. So I would say this is not even the goal at this point, maybe until we have really a compelling reason that all the other approaches are bad, which I don't think is the case. Now, maybe still an analytical reason for putting doubt on many words, at least for me, is the following. So I find the many words interpretation very interesting and attractive, and for several reasons, because, for example, it doesn't give up unitarity, but it also has aspects which, at the end, I cannot live with. And one of them is, I related to what I said before about time. And I try to make the point that time is one of the concepts which are not properties of the system we are describing, but also, at least to some part, properties of the agent, of the observer, or me, who is describing the system. And therefore, the information that we have about the system plays a very important role. And for me, the quantum state that we assign to the system could as well be, I'm not saying it is like that, but it could as well be just a description of the knowledge we have about the system, and therefore be something about me rather than the system itself. And I think this is a viable option. And if we take this option, it's of course nonsensical to attribute the quantum state to the whole universe, because in this view, the quantum state is always about, at most, the relation between the system and me, but not about the system itself. So that's a reason why, at least, I wouldn't want to believe unconditionally in one of the interpretations. I want to keep the option open that the quantum state can be understood in this information theoretic way. And at the moment, this is, for me, a very attractive option.
Okay, let me be a little provocative, and because it's late, a little indirect. So 30 years ago, Francis Fukuyama, the political scientist, wrote a book called The End of History. This is in the wake of the fall of the Berlin Wall and the fall of communism. And in the 30 years since then, he's had a rough ride for all the 9/11 and the credit crunch and the current crisis in Ukraine and what have you. But Fukuyama gets a bad run on this, because his thesis wasn't that bad things weren't going to carry on happening. It's that this was the end of the ideological fights as to what the form of government was going to be. That after the fall of communism, there was going to be lots of dissatisfaction with liberal democracy. There was going to be lots of problems in liberal democracy. Lots of people would complain about liberal democracy, and there'd be little windows of objection to liberal democracy. But there wouldn't be a big mainstream ideological competitor to liberal democracy in the politics of the world. And I think, in a certain sense, the same is true for the average interpretation in modern physics. So Lev quoted I wouldn't take this survey very seriously, but it's a nice starting point. Lev quoted the survey back in the first session, saying that only 6% of physicists who were surveyed believe in the many worlds theory. But it's also true in that survey that 82% of people surveyed said that superpositions of macroscopically distinct states were either in principle possible or would eventually be realized experimentally. And 78% of physicists surveyed said that the observer is a complex quantum system or should play no fundamental role whatsoever, or plays a fundamental role in the application of the formalism, but plays no distinguished physical role. And I think if you'd ask most philosophers of quantum mechanics, and if you said, well, I'm committed to the fact that macroscopic superpositions are realizable, and I'm committed to the fact that the observer plays no distinguished physical role, they'd say that you're extremely close to the core content of the many worlds theory. If you look at the way people actually use quantum mechanics, I mean, physics is huge and pluralistic, and I'm generalizing, and I speak more of the areas I know better, which is high energy physics and quantum field theory. But if you look at how we use quantum mechanics, we don't collapse the wave function. We certainly don't collapse the wave function in a dynamically substantive way. Usually we don't need to model the measurement process. If we need to model the measurement process, we include as much of the apparatus as we need, and we play things out unitarily. We don't appeal to the correspondence principle to make the connection to the classical. Normally, the quantum classical transitions is unproblematic, but if it matters in the details, we do unitary decoherence theory. We treat the world as emergently probabilistic in the sense that we apply the Born rule at the macro level, but at the micro level, we'll use superpositions as much as we like. We'll use representational language all the time. We'll talk about entangled states. We'll talk about preparing entangled states. The de facto practice of physics is tacitly committed to the great majority of the core claims of the Everett interpretation. The substantive claims that physicists make that are by the Everett interpretation, I'm sure are entirely sincere, but they're as much, I think, a dissatisfaction with what the formalism is doing as anything else. I think a foundational conference like this, where people care deeply and abidingly about the issues, is always going to be the exception that proves the rule. The question asks, why is the Everett interpretation not the consensus? I want to make the case that it kind of is.
To go into politics.
All the interesting ideological debates, right?
Thank you. Okay, so thank you all of you for these inspiring comments, and we have a few minutes before they close the gates. So I think you actually wanted, as well. And please use this because otherwise I cannot record you.
I'm going to be a bit provocative. Because I've been present in discussions about free will and determinism. And frankly, this is teenager philosophy. A teenager hears about determinism and then they're shocked. They say, oh, what happens to my free will? Well, let's go down to details. If fate determines all directions, then you have presumably no free will. But then think of the opposite. Suppose chance, there's no determinism, and chance determines your actions. That's even worse. I mean, tomorrow morning you wake up and you murder your family. Why? Because you're free. Because you're not determined. Of course, this is not the freedom that we want. So I think Professor Wallace said it basically. I think that free will cannot and determinism are orthogonal issues. They shouldn't be put. This discussion should be buried. Free will, what it actually means, I think, in my opinion, is that your actions are determined by the structure, by your own internal structure. Okay, and the fact is that it's true. All of us, all our actions, for all living organisms actually, are determined by the internal structure. And so in fact, not only do you have free will, but you have no choice but to have free will.
Unless you're locked up.
And even if you're locked up, you can choose which part of the cell you're in.
Okay.
Thanks. What's freedom?
Yeah, but he made some of the people happy. There is free will. Please.
Yeah. So I would like to. You can stand. Very well. Maybe I should.
He's gonna see you.
Oh, the camera is going to see me if I come closer. Well, okay. So I'd like to connect with what you say. I think that unitarity and so on are believed by most physicists and so on, but it's not necessary. I think, as Valia said, that all of these worlds actually exist. Isn't it enough that unitarity is preserved for the distribution, that it is
that the quantum state that we used to talk about is the parallel of the Liouville equation. So it just tells us about the distribution of what really happens.
I have my problems with that, but in a sense, in terms of the why this is a consensus, once you've accepted all of the vocabulary and machinery of unitary no-collapse quantum mechanics, whether you further want to utter the sentence and all the world's physically real, it's kind of clear why that's not going to make a lot of difference to physics. The physicist who makes that claim is not going to have much that comes from it. I mean, any more than the astronomer who theorizes about planetary formation and discusses how that might play out in distant galaxies. If two astronomers do all of the same astrophysics about that sort of thing, and then one of them says, and those planets all in different galaxies exist, and another says, but of course this is just a model, science is all about direct observation, we'll never observe them, so don't take this too seriously. Again, that's going to be the kind of conversation over drinks that's not going to affect the playing out of physics. So for boring and standard scientific realism grounds, I think if you accept the sort of structural assumptions being used in the Everett interpretation, it commits you to the existence of worlds, but it's kind of unsurprising that commitment is kind of only varyingly run with by physicists. If there's ever a situation where people want to say, well, the worlds aren't physically real, therefore we need to turn off the superposition principle at some point, that would be different.
Thank you. Other question?
So about also free will, I have a question that actually the person in the purple chat asked half of it. Because of the reason that Professor Allori said, I also believe that randomness can't have anything to do with free will. But you were talking always about the fact that you thought about free will as the ability to predict what someone is going to do. But maybe, like many other things in physics, it is also about the frame of reference. So, for example, in my consciousness frame of reference, I have a free will because the way that I make decisions in my consciousness is aligned with the idea of free will. But in some other supercomputer frame of reference that can predict everything or almost everything that I'm going to do, I do not have free will. So maybe free will is something that have a lot to do with some extension of the idea of a frame of references.
Okay. So if Tim wants to ask a question, maybe
the white shirt there. So that is basically saying it's a relative statement. So anybody wants to comment on this relative?
Comment on that,
yeah, please.
Yeah.
Yes, sir. There is another microphone over there.
we have enough microphones.
Yeah.
There is another one, but okay. So
I just wanted to actually say that I very strongly support that statement because that's in line with this, I think, belief that at least I have and try to somehow explain that when we describe a system in physics, for example, in quantum theory, this may as well be about our relation to that system. And that is also connected to the question you, or maybe the comment you made about the determinism and whether this has anything to do with physics. I think it's a relative statement because if for me the world is completely deterministic, then I don't have the free will. But no, if it's for me, it's just, it could be deterministic as seen from the outside, and then I can still act. And from my reference point, to take the terminology that was introduced, which I think is a good terminology, I would still have free will in that sense. But it's a difference whether the world that someone describes from the outside, which includes me and what I see, is deterministic, or whether my description of the world is deterministic. I think this is exactly this reference point, and we have to distinguish that. And I think you made a very good point in saying that this is relevant.
Yeah. Tim had a question.
Tim.
Yeah.
Okay, please.
Comment about this free will. I mean, I completely agree with what
David said, although
We just stop and pause on that moment. Doesn't happen very often.
Not the last thing he said, but the earlier thing he said. And just like say a word, if we were at a philosophy conference with experts in moral theory who talked about free will, and there was an open thing at the end, and they say, by the way, what do you guys think about quantum mechanics? And they went down and they said, oh, I think this, I think that. And you thought, but how hard have you studied this? There's something very strange about this. I just wonder, people who think it's obvious that there's some conflict between determinism and free will, have you read Locke? Have you read Hume? Have you read any of the classical analyses, conceptual analyses of what the term free will means? It means a bit more than just that your actions come from inside you, right? If I sneeze, that action comes from inside me, but it's not a volitional act, right? Some of our acts are volitional, some of them aren't. We deliberate about some things and choose. We don't deliberate about some things and choose. But this is something that's very well trod ground. And the idea of compatibilism between determinism and free will, which is really indicated by the fact that giving up determinism doesn't help you, which is what everybody says. They say, oh, there's a big conflict between determinism and free will. You say, well, give up determinism. Well, that doesn't help you. Okay, you've made a conceptual error. And compatibilist free will is not, as Nicolas said, an invention. It's the result of people thinking carefully on the basis of how we use these terms, what they mean in everyday life. And there just isn't any conflict between determinism and free will. So if you really care about free will, fine, but then do the work to read a very long philosophical tradition of people who thought carefully about this in a way that physics just doesn't make any real difference to. Especially if you think there's no conflict between determinism and free will. Doesn't matter whether you're talking about Newtonian physics or fantasy Democritean physics or whatever. But do the work.
Yeah, if I may, I agree that we are not, or I am not a specialist in free will. I did not read all the books, but I read some of the books you mentioned. But I also read a book that I'm sure you also read by Rob Kane. And so also among the philosophers, there are different opinions.
I should also tell you that physicists are allowed to talk about everything.
They can, and people listening can make judgments about them on the basis of what they say.
Just as an answer, because you also addressed me. So, I mean, I think at the beginning, I have no idea what free will is, and I'm not a philosopher, so I don't want to pretend I know what free will is, and I would guess no one knows it, but there is this connection, I think, which we have to address. I think if we discuss this question about free will, we have to bring philosophers who know about that and physicists together. And actually, there are many conferences that I've also attended where these things can be discussed, and everyone in this conference usually admits that he doesn't know, let's say, the subject of the others in detail, but this is kind of mutual. And I think if you now, for example, talk about the notion of determinism, then from a physics point of view, this often also sounds like too simplistic if, let's say, someone who is not a physicist talks about that. So I think we really need to bring the two communities together and allow ourselves to talk about that, knowing and understanding that we don't know, let's say, all the literature of the other side. Now, in the particular case, for example, of determinism, I think there's also a huge literature in physics what that even means. And I think even this concept that determinism could be relative to another system is something I often don't see at all in the philosophy discussion on free will. This is completely ignored. So I would now say, as a physicist, this also sounds strange to me. If a philosopher talks about determinism but doesn't say what it is, I'm not even sure is it now supposed to be an absolute notion or is it relative. And I mean, in physics, we of course have thought very deeply about relativity, obviously, and relative concepts. For example, I mean, yeah, I don't think I need to make examples for that, but like just this question of whether we have determinism or not. is not just a binary question, which I can say in this theory you have determinism, in this we don't. I think it depends on how you even define the physical theory. What is, for example, the Heisenberg cut we put in quantum theory? That depends, that influences whether you call something deterministic or not. Do we think of how do we treat the hidden variables? Do we already from the start assume that time goes forward, or do we leave that open? There's a whole community discussing causality in physics. This is all connected to that. So I just want to say that there is also a very rich framework in the physics community which connects to that. And I would just support like more discussions between philosophers and physics. And clearly, none of the two should pretend to already know the others. So in that sense, I agree with that.
We get a support from philosophers.
Well, just a quick comment, I guess. I mean, I basically agree with Tim, but a bit of clarification is perhaps relevant. I mean, I wasn't saying, and I don't think Tim was saying, that the only philosophically acceptable move on the landscape is the compatibilist move. I think that move is right. I think that's what Tim does as well. But plenty of serious people in that framework have thought in other directions. If you were inclined to some of these other directions, then free will starts looking mysterious, and then maybe there's space to explore and see where it gets. If you're basically happy with a compatibilism of a Strawson's or Dennis or whoever's style, then at that point you're probably going to say, by all means, get on with it, guys. I probably haven't got much to bring to the table other than being the gadfly who says this is all fine. The other quick thing I was going to say to Tim is, well, it could have been worse. It could have been consciousness.
Now that you mentioned it, look, it seems to be that the gates are going to be closed in like 15 minutes. I think it's a good time to close. No, there is an urgent question. Anyway, there are no answers in this panel. Okay, go ahead, last question, and then we run to the gates.
They are all a result of evolution. Our decision to live now or to live in 5 minutes is not different from a decision of an animal to go to bark or to bite. So individually, in one sense, because we are all we do is a result of evolution, is a result of creation. It is deterministic. But on the other hand, our decisions are individual. This is a matter to biologists, to other sciences, to the science of philosophy, to sociology. Why do you think physicists should produce a model that will answer to this question? Now, Yaron said that physicists can talk about everything. But my question is, should they?
Maybe they should not, but the relative statement sounds good enough to me. Okay, but I think, yeah, it was really very, very interesting. Thanks a lot, and it means a lot of stuff.